Thank you for having me today to present to you zooming into the quantum regime, the EHT and quadratic gravity. This is joint work together with Jesse Daas, Kolja Kaupers, Frank Saueressig and Heino Falke, where Jesse and Heino are also at this conference. So, we are going to look into quadratic gravity, an extension of Einstein's general relativity, and into the phase space of black hole-like objects in the theory, and in their imprints on shadow observations as by the EHT. And finally, we conclude with some outlook. So, now we are very proud of these two great pictures of black holes from M87 star and Sagittarius A star. And among all the interesting features and aspects in these images, I just want to highlight two, namely that we have in both cases a ring-like shape and a central brightness depression. And this brightness depression is what we are going to use in this talk. And we're going to use it in the context of quadratic gravity. So our known and loved general relativity is the fundamental force in physics, which has been tested over the largest scale, over the largest magnitude of scales. So even more than quantum electrodynamics. But we know conceptually it is still inconsistent in the quantum regime. So we need some quantum gravity theory. However, constraining them is quite hard. At least we know that any such proposal of quantum gravity should, in the classical limit, reduce to GR plus some corrections. And these corrections shall be in form of curvature term corrections. So if you look for GR in its action formulation for the Einstein-Hilbert tensor, that you add more terms. You do not just have the Ricci scalar, which is the first term and first order in curvature, but you add more terms, higher order in curvature. The first correcting terms would be quadratic, and therefore implying that it is fourth order in derivatives. So we're looking for this first order correction for quadratic gravity and ask ourselves whether such corrections to the theory of gravity can be constrained from black hole shadow observations. To be a little bit more technical what quadratic gravity means, here you see the action in 3+1 dimensions in full beauty. It's the most general form which contributes to dynamics. And in addition to the Einstein-Hilbert term, we get a contribution parameterized by alpha and beta, quadratic and curvature terms, namely the Weil tensor contracted with itself or the Ricci scalar squared. As a quantum field theory, this would actually be fine on its own, as it is renormalizable at the cost of introducing 2 additional degrees of freedom, which we will encounter in the next slide. What happens now if we have this theory? Well, the dynamics changes, and we get an extension to Einstein's field equations. Those can be written in a compact form, and now we get this alpha and beta dependent additional terms. Solving this is not easier than the Einstein equations, but the opposite. However, we are interested in black hole-like solutions, and thus in vacuum solutions, where the energy momentum tensor is 0, and this makes life a little bit more easy. In particular, we look for analogs of Schwarzschild black holes, so for static, spherically symmetric, and asymptotically flat vacuum solutions. This very much constrains our metric and our degrees of freedom, as in GR. We just have 2 degrees of freedom here. We have the time and the radial component. Still, solving the equations in full generality analytically is not possible, but we can solve it for large distances. For large distances, we are in the weak field regime and can linearize the theory. And what we get is U-Carver terms. That was already found by Stelle. So on top of our Schwarzschild solution, we get 2 U-Carver terms with range M0 and M2, and given by amplitudes S0 minus and S2 minus. These ranges are suggestively named M because these are the new particles that we introduce in our theory, a scalar and a spin 2 one, and their masses are given by the parameters beta and alpha. Having solved and control over the large R regime, we now want to find the solution over all spacetime. So we have to numerically integrate inward also until the center. And the center is decisive for what kind of solution we actually have, what kind of black hole. For small r, we can again apply some analytic technique. We can use a Frobenius ansatz, so an expansion in the radial coordinate, which normally gives you some asymptotic series, so something which does not converge, but gives you the scaling coefficient, the scaling exponent, so we get how the solution scales very close to the center. What we can do now is we can match our numeric solution close to the center with these potential sets of initial exponents, and so classify what kind of solution we actually have. And such a classification looks like that. Instead of only having the Schwarzschild solution, as is given by Birkhoff's theorem in GR, we now have a rich phase space. Here you see a slice of this higher dimensional parameter space. And you see that we have these colors giving what we call the type 1 solution. We have in yellow type 2, and we have also in black type 3 solutions. And if you look very closely, there's also one dot in the center where alpha and beta are not important because we have set the amplitudes to 0. And so they are not important. We just have we recover GR, and so the solution we have is Schwarzschild. But apart from Schwarzschild, we have rich behavior around. Here you see these type 1, type 2, and type 3 sample solutions, namely f and h of r as a function of the radius in the logarithmic plot. You see different scalings, different behaviors. 1 and 2 belong to naked singularity solutions, so without horizon, while type 3 belongs to wormholes. You see that the solution ends at a finite value of r, and you can glue a copy of this spacetime on the other side, so you actually get a wormhole geometry. There's a Z2 symmetry in the system. So quite a big amount of wormholes over there. You now might wonder why we actually have 3 colors for type 1, and this is because we can subdivide them, namely as a function of the effective potential. The effective potential for light-like geodesics, so for light rays, is especially important for us when we now go to towards imaging a black hole. We have the effective potential for Schwarzschild and sample solutions for 1a, 1b, and 1c, we classified them. So 1a still continues to smaller values of r, but only decreases. 1b increases, and 1c even increases above the level of our Schwarzschild maximum. So the maximum here tells us the position of the photon orbit. And now we have something which goes even larger. So this will make an effect. And we're having a closer look. For looking for shadows and pictures, we actually need to specify some light source. And here we use a very simple emission geometry, namely some accreting infalling gas, which is freely falling on a stationary geometry. And this gas emits light rays. Okay, and their geodesics can be classified by just one parameter in spherical symmetry, namely the impact parameter B. So if I have a large impact parameter, so if I'm far away from the black hole, it actually corresponds to a low total specific energy. And in this sketch of the effective potential, I'm in the lower part. While if I'm very close directed toward the central object, then I have a small impact parameter and I'm more in the upper part of this regime. Okay. If we have this gas, and this gas emits radiation, some of this radiation is outward directed. And outward directed radiation can come to the observer as long as it is emitted outside a potential horizon. Inward directed radiation, however, can only reach the observer at infinity if it is reflected somewhere in the center. And so we have our Schwarzschild angular momentum barrier, and additional with 1c we also have some central angular momentum barrier, which is even higher than Schwarzschild. There are also type 2 solutions where the effective potential actually diverges, has no finite value. And so these light rays Ingoing ones will not be observed but reflected, and this will show in the pictures. We start with the Schwarzschild geometry. Here we have the intensity as a function of the impact parameter, and also the image plate where intensity is given by color. And well, for 1A and 1B, nothing interesting happens. Also for wormhole solutions, we get the intensity profile from Schwarzschild with a large brightness depression. So we have our shadow over here. This is indistinguishable from Schwarzschild. However, if we go to type 1C, we are now in the situation where some of these ingoing light rays are actually reflected. So we have a bunch of impact parameters which are contributing now, and which make some contribution to the intensity. Actually, a lot of contribution, as these paths of these light rays, due to this spiral movement, actually have a long path, and therefore accrete a lot of intensity. But still, we have some range of impact parameters where we have no intensity. So we have some small shadow around. And as a cherry topping, we still have a small peak at the position of Schwarzschild of the photon orbit. This means that we have an intrinsic ruler in our image. And if such a situation was in nature, we do not need two independent measurements of mass and distance because of this intrinsic ruler relating the mass to the angular size. Finally, we have type 2 solutions. In type 2 solutions, every light ray is reflected. We have no shadow in the center, and so we already can exclude these part of the phase space from the ngEHT observations. So in summary, what we can say is that we have done a parameter survey for these black hole-like objects, Schwarzschild-like objects, global, static, spherically symmetric, and asymptotically flat in quadratic gravity, and there were more or less no black hole solutions, but most were naked singularities and wormholes. Also in these cases, without horizon, we have a shadow, which is sometimes underappreciated. And in particular, for our quantum gravity theories in the classical limit, we find observable differences at the horizon scale. And we can derive constraints from ngEHT observations, which is quite exciting. What we want to do next is to look for more sophisticated emission models based on GR-MHD, and for looking for better ray tracing algorithms, which we need if we always also go to the rotating case. With that, I would like to thank you for your attention, and I'm happy to have questions either in the Slack channel or via email. So, thank you, and see you hopefully soon in person again. Bye.